Acid-base titration part 2, chapter 8. So once again, just some terms that we need to remember. We've done and we talked about a strong acid and a strong base titration. And today we'll be looking at a weak acid with a strong base titration. So what are we going to look at today? Well, to perform our calculations, we're going to have to use two steps. We're going to do a stoichiometry step, and we're also going to do a equilibrium step. So we're also going to need to recognize the shape of a weak acid strong base titration curve is going to be different than a strong acid strong base. We'll need to figure out where the equivalence point is and also where the buffering region is. So once again, weak acid and a strong base, and we're going to look at it from 4 different situations before we even start the titration. So just what the concentration is of the weak acid, before the equivalence point, at the equivalence point, and then after the equivalence point. So once again, the calculations are a little bit different. And the reason why they're different is all because of this ion here, right? This is the conjugate base of a weak acid, so it's going to affect the pH. And so we're going to do it in 2 steps. We're going to look at a stoichiometry step. We need to look at this step because we need to find out how much of my acid is going to be neutralized by the base. That will tell me how much acid I have left over, and it will also tell me how much of the conjugate base is formed. And then we'll do the equilibrium step. So here's our situation. 30 mils of 0.25 molar hydrogen cyanate and a 0.1 molar solution of sodium hydroxide. From the data table, the Ka of HOCN is 3.5 times 10 to the negative 4, and there are our 4 situations. And we're going to focus on before titration. No stoichiometry step is necessary because there is no neutralization that's occurring. And so we're just only going to look at our ice table. Kind of simplified the ice table a little bit. I left out the H2O, so we're not forming the H3O+, we're just forming H+, but they mean the same thing. So we have a 0.25 molar solution, minus X plus X plus X for the change, and at equilibrium. And the nice thing about doing the Ka acid-base equilibrium is very similar to the KSP equilibrium, very similar to the equilibrium section. So we've done this many, many times. We set up our Ka expression, we sub in our values from the equilibrium section, that's the one that we're most interested in, and we're always going to check our assumptions. Not to worry, I want you to write them down, but for our purposes, the assumptions will be valid 99.999% of the time. But I still want you to write it down to check, because in university, if you run into this, they could be trickier than I am. So we sub in our values, we solve for X, and we get our hydronium ion concentration. We're looking for pH, so we'll take the negative log of it. And our acid, before we start titration, has a pH of 2.03. Now, second point. This is the more complex one, before equivalence point. Before equivalence point, we're going to look at a stoichiometry step. So we're going to figure out how many moles of base we have. And remember, to figure out the number of moles is the concentration multiplied by the volume. And I'm just going to grab a pen here, I think. There we go. Okay. And now our next step. This is the amount of hydroxide that's going to react with the H+. All our reactions are going to be a nice 1-to-1 ratio. And so if we have 0.001 moles of base, we're going to lose 0.001 moles of acid. So we start off with that 0.0075. We're going to lose 0.001 because it's going to react with the base. And this is what we have remaining in moles. So now neutralization has occurred. And we did not neutralize all of our HOCN, so we're going to have some of that left over, which we care about. We've produced some of our salt, the conjugate base of a weak acid, that we care about. We've also produced the other half of the salt, but this one is the conjugate of a strong base. We don't care about it. We're not going to worry about it. and of course there's always water going to be present. So first of all, let's figure out our concentrations. Well, we've got the number of moles that we started with, the number of moles that reacted with the base, and you'll note we have a total volume, and so this is our concentration right here. Concentration of our OCN negative from our 1-to-1 ratio, our total volume, and that's the concentration of our OCN. So this is our stoichiometry step. We need to figure out these concentrations because we're going to put them into our ice table. So now, ice table, equilibrium step, we'll sub in our initial values. There they are. Our change, nice 1-to-1 ratio, minus x, and we don't care about the water. And at equilibrium, this is what we have. And once again, we'll always kind of double check to see if our assumptions are valid, but for purposes of this course, they will be valid. So we're going to write our Ka expression, done that before. Now you'll note that in class, there are times I gave you two options. You could write it as a Kb, or you could write it as a Ka. So in this PowerPoint here, I wrote it as a Ka. We'll sub in our values. We find out that our hydronium ion concentration is 2.28 times 10 to the negative 3, and we want our pH, of course. So after we've added that 10 mils of base, our pH has changed, and it is now 2.64. And of course, let's always check our assumptions just to make sure they're valid, and our assumptions are. So this is before our equivalence point. So key things to note. We've got some of our acid still being present because we have not neutralized all of it. We've also produced some of the conjugate base. And these two now are going to be involved in our ice table. And if you remember the KSP, kind of looks like a common ion problem actually. Okay, so now let's jump to at equivalence point. You'll notice we have 30 milliliters of our acid, and at equivalence point in this case we have 75 milliliters of our base. Once again, that's because our concentrations of base and our concentrations of acid are different. So at equivalence point, we're always going to start with our stoichiometry step. Remember, the whole idea or the definition of equivalence point is equal number of moles of acid, equal numbers of moles of base. And if there's equal number of moles of them, that means that all the acid is used up, all the base is used up, so the only thing that's remaining is our sodium ion, which we don't care about, our OCN negative, which we do care about, and our water. And the OCN, once again, conjugate base of a weak acid, that means the OCN is going to react with the water, or it's more technically, we're going to say it hydrolyzes the water. And when it hydrolyzes the water, we produce our base. And once again, if we're looking for a base in our equation, we can't use Ka anymore. We need to use our Kb value. So at equivalence point, our new concentration of OCN negative, always remember, we've mixed two solutions together, so we need our total volume. And we're going to put them into our ice table. You'll notice our ice table looks different from before equivalence point. This time I have the OCN as my reactant, and there's no acid remaining because we're at equivalence point. Our negative x, plus x, and plus x, our values at equilibrium. This time we're going to write our Kb expression, and remember we can find Kb if we know our Ka, because our Kw is always going to be 10 to the negative 14. So there's that calculation right there. So Kb, very, very small, well, really relatively small, 10 to the negative 11. So we write our Kb expression, we sub in our values, we'll check our assumptions, no problem there, our assumption is valid. And so as we solve, that is our value for our hydroxide ion. So we're figuring out our POH, and then we just need to convert it into pH. So pH, you'll notice at equivalence point is not 7, but it's 8.16. And that's because we're dealing with a weak acid and a strong base titration. So let's look at the last point. How about after equivalence point? Now remember from the slide before, our Kb value is somewhere in the neighborhood of 10 to the negative 11. That's relatively small. we're not going to be producing a lot of hydroxide ion from the hydrolysis of water due to the OCN. That's important. So at equivalence point, after equivalence point, this is the number of moles of H plus or acid that we had initially. Now, this is the number of moles of base that we're adding. So we're adding more base than we have acid. So after the reaction, we're going to have leftover base, leftover OH minus ion. We've got our total volume here. And now, to calculate our hydroxide ion, we have this calculation here. We did not add on the hydrolysis of water that occurs due to the OCN negative. Because remember, our Kb is really small. That means we're not going to produce a lot of hydroxide ion from the hydrolysis of water. Most of our hydroxide ion comes from the leftover base. So it'd be 0.0045 plus probably somewhere times 10 to the negative 8 worth of hydroxide. So we can ignore it. And so nice straightforward calculation, pH 11.7. All we need is our excess hydroxide ion. We don't need to worry about the hydroxide ion that comes from the hydrolysis of the OCN. Okay, so let's take a look at our titration curve. It looks like this, and you'll notice here, this is our equivalence point. We have a flat region here that we call the buffering region. We're going to talk more about that later. And at equivalence point, our pH is not 7, but rather it's higher than 7, greater than 7. In our case, it was, I think, 8.4 or so. And that is the titration of a weak acid with a strong base. Once again, these are the things you need to understand to master the unit.